Hello, everybody, and I'm very happy to be here. Today, I'm talking about order-preserving bilateral lookup, or we call it projection query. I'm Azam, and I work, now it's 3 years at Consensys. We work in Linea team, layer 2 scaling solution developed by Consensys. So, what happened in layer 2 and between layer 2 and layer 1? All the stories start from arithmetization. On layer 2, you have EVM bytecodes that arithmetization would take them and convert them to columns, tables, and constraint between tables, between these columns. These tables, then they are input to the prover, where I work, and we generate the proof from this table, and the proof is sent to the layer 1 as a transaction. There is a contract on layer 1 which verifies this proof, and if it gets verified, it means that everything on layer 2 was correct, and the state can be transit to the new state. So as I mentioned, arithmetization is a mathematical modeling of EVM behavior in the language of columns and constraint between these columns. For example, if you have function h, which receive input x and the output is y, so you start with a column x, which kind of encode this input. Then you have intermediate columns, which in fact, depending on the operations that are happening in the function, you continue until you arrive to column y, which is the output, encoding of the output. And then there is this constraint between the columns to show that the operation, the mathematical operation, that function is carrying on done correctly. As a simple example, if you have a bunch of transactions, this transaction, the balance, the value, they are stored in some columns like this, and when you send a value to another account, the way you get your you understand what is the new balance is this, by this constraint that, okay, I have the old balance, I spend this value to another account, and I pay this gas that I should reduce from my old value, my old balance, and then I have this new balance. A more realistic example is what is happening on Linea, is about hashing of the RLP of the transactions. For example, here we store the RLP of the transaction in a column which is called lim, and as you see, hash number 6, all of them are related to the same transaction. And then you have another table down that shows that what is the result of the hash for example, hash number 6 for transaction 6. We have different type of constraint. The most common one are lookups, which means that column A should be included in column B. I would come back to this special constraint because it's the topic of the talk. You have local constraint, which means that if you consider the first row of the columns, then you expect some constraint between these elements. Global constraint, which kind of true between all the rows of the columns. Here you see that I expect, for example, at row I should be the sum of row I minus 1 and row I minus 2. And more constraint like permutation, and even custom constraint like hashing. So let's focus on lookup tables or lookup queries. Here you see this example that we expect, in fact, that S be subset of the T. That's why I show it with S. S is a subset because it just has 2 and 0, and 2 and 0 are inside of the T. So S is included in T. It's a positive lookup. But for example, S prime is not, so it's a negative lookup because 32 is not in the T. T is from 0 until 15. So as a positive lookup between S and T, and as a prover, I want to prove that indeed S was in T, and I'm not lying. How we check it? The first thing that we do is that we generate a new column, which we call it multiplicity column. And you say that for each element of the T, how many times it has happened in S. For example, for 0, you have 5 times in S, and for 2, you have 6 times, and the other 0. Then we generate extra columns, which what we call them accumulator, S sigma and T sigma. And they just accumulate the element of the S in a special way. For example, you accumulate an element of the S in a fractional way here. And at the end, you expect that the last row should be equal. Why this should be the case? Because here in the accumulation of the S, you just accumulate all the element of the S, and the other side, you accumulate the element of the T, but considering their multiplicity in the S, which is the same thing. So they expect that they should be the same. If you open the last row, it should be enough. Applications. In many teams, when they write the constraint, because EVM is a very big, very complex system, so you have kind of a lot of modules which do a lot of different tasks, and each of these modules I can translate them to tables. And sometimes you want that, okay, I want some elements from this table to bring them to another table and do extra operations. So I want these columns, these elements from these columns to be included in the other one. It's a lookup. I mean, what they use is a lookup. But there's a security concern here. And the reason is that, okay, in the second table, I may add new elements which are not from nowhere. So how do you guarantee that I don't cheat? And these data are really from the previous columns, previous modules. Or another way to cheat is that you change the order. You can change the order of the element. For example, here you see that it's pink, blue, but the other side, it's not the same order. And maybe I cannot immediately say that what kind of attack the adversary can use here, apply here, but definitely you should never leave the door open for the attacker. So what we believe is that we need a kind of bilateral relation to, for example, prevent this adding new elements. It should be both sides that, okay, whatever I have in this side, I have the same the other side, and vice versa. And we also need order preserving to be sure that the order of the element was not changed. The way we do it regarding the bilaterality, we use 2 columns that we call them filter. And we just say that, okay, I expect that in these positions, it should be exactly the same as the other column. Whenever you have, you expect such thing, you put 1, and if you don't care, you just put 0. So when it is 1, it should be really the same as the other one, the other table. Regarding the order, so it was for bilaterality. And like this, you could not add new elements. Regarding the order, some teams they are adding a new column that they call it order column. And they say that, okay, what order I expect? And then they apply lookups. This can work, but of course you need to add these extra columns to specify the order that you want. What we do in the prover team of Linea is something that we have a direct query. We have a projection query. And the way that we ensure the order is we do it during the building this accumulator columns, because anyway you had it even in the lookup side. So we impose the order during the accumulation by adding this random element alpha, and whenever your filter is 1, the power of alpha would increase. And by this, the order is preserved, because if you change the order, the power of alpha would not be the same in the both sides. And then at the end, you, again, similar to lookup, you just need to open the last row and check that the last are the same. And by this, you are sure that the elements were the same, the order was the same. So to give you a visualization, I can say that projection query is like a one-to-one arrow between these columns, something like this. While lookup is many to one, and it leaves a lot of open space for the adversary. As I mentioned, you can have projection query proper security that you expect, in fact, from projection query. You can also have from lookups, but you need to add more columns. While in projection query, you have it with less columns. Okay, what I mentioned here is that you just need to check the last row. But how you are sure that accumulation was correct? Okay, you accumulate until that you arrive to the last row, but how you are sure that the accumulation was correct itself? The way the magic comes from polynomials, polynomial commitment more precisely. In fact, we interpret each column as a polynomial. For example, you can say that the elements in the columns are the coefficient of the polynomial, as a simple example. And by this, the constraint between columns would be a relation between polynomials, simply. And then you use polynomial commitment. What is the polynomial commitment? You commit to the polynomial, which is a kind of digest of this polynomial, and represent your polynomial in a very short way. And then you also can open your polynomial in a given point and prove that your evaluation was correct. And also the proof is short or succinct. So what I want you to remember from this slide is that the commitment, which is a kind of represent your polynomial, is short, is succinct, and also the proof of opening, proof of evaluation is succinct. And the next magic comes from Schwartz-Zipper lemma, because it says that if you have a general relation between polynomials over a big domain, for every x, for example, here, you just can take a random element from the domain, like alpha, and you just evaluate the relation for this single random value. And if it is satisfied, you are sure that it was satisfied for every x. So how these two tools help you, this commitment, succinctness, and this Schwartz-Zipper lemma, because now you don't need to check the relation between, for the accumulation, you don't need to check that for every row that, okay, it was really the accumulation so far from the previous line. You just check the, by Schwartz-Zipper lemma, you just check it on the random point, and you know that the proof was, the proof that you are saying that I evaluated in the random point is short also, is succinct. So this is how you prove, in fact, your projection query was done. More applications of projection query. As I said, projection query, the first time we designed it due to this security concern that we had, that adversary may add new data or change the order. But later we just came up with more application like column rotation. That, for example, you have here a column, a row that you can rotate it, and it would be the column in the other table. And you prove that you have done this correctly, this rotation. It is really rotation of this row. Where we are regarding this query and in general in prover, now we are in the distribution phase, which means, what does it mean, the distributed prover? For the moment, provers are like very heavy machines that take all the trace. And when I say the trace, for us, it's like big tables, a lot of big tables. And they have to process these tables and generate the proof based on these tables. But these tables, as they are a lot and very big, so the prover is a very heavy machine. What we aim for is that, okay, instead of one big machine, I have a bunch of small machines, and I break this trace in this sense of the table to small tables, and I give each part of the table to one machine. And by this, they can process even the bigger traces. So it's increased the efficiency noticeably. This is the architecture that we have really. And as I said, in the sense of the query, when you break your tables to two tables, then you have to say that the relation was true between all these tables together. Thank you, and thank you for listening to me. If you have any question, I would be happy to take.
Any questions? All right, let's give an applause again.
Thank you.